Thanks for inviting me to speak. I'm a Norwegian student. In the past, I studied music technology. Now I'm studying computer science. And recently, I've been creating a piece of software where you can input two sounds and say, I'd like the first sound to sound like the other sounds. And this is achieved through using cross-adaptive audio effects combined with artificial intelligence methods. And I'll explain how it works in a bit. But first, let's listen to some sounds to get an idea of how this works and what the software is capable of. I don't know if the sound works, but let's try. Here's the input sound. Quite nice. It's easily shapeable. And here's my target sound, a drum loop. So I want my white noise to sound like the drum loop. So my software takes these two sounds and processes the white noise so that it sounds like the drum loop. For example, like this. This is one output. Now, when I say this sound was processed, I mean that an audio effect is applied. And in my experiments, I've been using distortion with a resonant low-pass filter. And let me illustrate. So to the left here, we have the white noise. And it goes through this audio effect with a set of knobs, effect parameters, if you will. And out comes this sound that resembles the drum loop. And in order to make it sound like the drum loop, we need to change the parameters over time. For example, to resemble the bass drum, the cutoff filter needs to be set low. And one moment later, it needs to be turned up for the snare drum. So control them over time, right? Behold my drawing skills. I'm using a cross-adaptive audio effect, these knobs will be controlled based on a second sound source, namely the target sound, in my case, the drum loop. So how do we use this sound to control those knobs? Well, first we need to analyze them. Analyze the sound. So we get a set of audio features, like, for example, noisiness, or spectral centroid, or pitch, maybe. And then we can connect these features to the knobs. And what you see here is basically the toolkit that one of my advisors, Øyvind Brandtzæg, created last year. And he has experimented with creating these mappings manually. And he found that it was actually hard and tedious. There are very many combinations. And remember, you also have to tune the weights. How strong is the connection from a feature to a knob, right? And you have to set an offset, like the default position for the knob. So he offered me this project where I should create these mappings automatically using artificial intelligence methods. And I love AI, so I was like, challenge accepted. I decided to use a neural network for this mapping. It's not that hard to explain, actually. The top nodes here are where the audio features go in, and the bottom nodes are where the knob values come out. And they have edges that connect the nodes. Each edge has a weight attached to it. This weight decides how much signal should pass through. For example, let's calculate the output of O1, the output one. We take I1 times weight 1,1 plus I2 times weight 1,2, and then bias times weight 1,3. This bias node is actually just constant. It always emits 1. And then we take this whole sum and pass it through an activation function. This activation function clamps our numbers between 0 and 1, so they become practical to work with for the knobs. This is a sigmoid function. Now, so the problem my AI is tasked with is creating these mappings. It has to decide which features to connect to what. And it can also add intermediary nodes, also called hidden nodes. And last but not least, it has to decide what weights, how strong should these connections be. But for my AI to experiment with this, it needs to have a concept of what's good and bad, right? We human beings, we can just we can run this signal and listen to the output sound and think this sounds like garbage, or maybe that's not too shabby. But our computer companions need something more rigorous, something mathematically well-defined. And in my project, I've been writing fitness functions. A fitness function takes in a candidate solution, a neural network, and it outputs a number between 0 and 1 according to how good this solution is. And 0 being awful, 1 meaning a perfect solution. One of my fitness functions is based on similarity in features between the two sounds, between the target sound and the output sound. So here we have two sounds, each having 3 features. And at a given time step, like here, at 6.466 seconds, we can read out the values for the features and compare these 3 values to these 3 values. And I do that by taking the Euclidean distance. And this distance is 0 if the 2 vectors are exactly equal. But if they differ, this distance becomes a positive number. And we want to optimize for 0, right? So for every time step in these sounds, we calculate the Euclidean distance. And we find the average Euclidean distance, which is what I call the average here. And if this average distance is 0, which is optimal, none of my fitness is going to be 1 over 1, which is 1. So perfect. If the average distance is 2, it's going to be 1 over 3. So that means 0.333, which is not that good. So now when my AI has a concept of what's good and bad, I can let it experiment with lots of different mappings and just try what's good, right? So I've been using a genetic algorithm to let my AI come up with good solutions. And first, it starts off with just trying random stuff. Just throw out many solutions, random neural networks, random weights, everything. And then for each neural network, we create the output sound, evaluate it, right? And the bad solutions, we don't care about. We just discard them. But the better solutions, the better solutions, they are more likely to produce offspring. These children are almost like their parents, but they are slightly mutated. They are variations of their parents. And these children might produce a better sound than their parents. And the children will be the population of the next generation. And that generation will, again, produce new offspring, which might be even better. So over time, that yields improvements in the best individual, as can be seen here. On the y-axis, we have the fitness value. And on the x-axis, we have the number of iterations, or the generation number, if you will. Now, this screenshot is this is a screenshot from my visualization tool that I created to ease the process of evaluating the results that my algorithm is creating. And I want to demo that for you. In this example, I'm using a synthesizer sound for input and the drum loop, as we heard before, as target sound. So let's have a look. Again, here's the fitness plot to the left. And to the right here, we have a slider for selecting a specific generation. And then we can see on the histogram how the population scores on the fitness function. We can see that it generally improves over time. If we scroll down a bit, we can select a specific individual in the generation that is selected. Now let's listen to some of the sound in the very first iteration, the worst iteration. Best individual, first generation. Skipping ahead a few generations, small improvements. Going to the last generation, where the best, according to my AI, is, where the best sound is. Let's compare it to the input sound, which was the synthesizer. And the target sound, the drum loop. above here we have a visualization of the neural network. Red weights are positive, blue ones are negative, and we can click nodes to inspect the weights and see what's really going on. And we can use these as parameters in the audio effects. Down here we can see how the audio features change over time. Red values means above average, blue means below average. And we can compare the features of the target sound compared to the output sound. You can see that they are somewhat similar. On the bottom, we have a horizon graph that shows how the effect parameters were changed over time to achieve the output sounds. I think that the techniques that I've used in my approach can be applied in, for example, mixing. Let's say that you have this jazz recording and you want it to sound tinny-like, right? So you have this song from the 50s and you want your jazz recording to sound like that. So you give it to the software. And you might want to optimize for constant parameter values, and you can do that theoretically. And you might also want to use it for crossfading. For example, you can crossfade from the input sound to the output sound, which is kind of a hybrid, and then to the target sound. I'm creating a small example just for fun to illustrate this. Listen. Oh, sorry. My software doesn't work so well for complex sound, like mixes of pop songs, but that's something I'm working on right now. I'm also working on making it live so you can use it on performances. Also, if you want to try this software, it's open source. You can find it on GitHub. You'll find how to install it on Ubuntu and on Windows. And there is also instructions for how to run your first experiments, such as the one you saw in the demo. And you'll get small explanations of the parameters you can use for running it. So here's the link to the GitHub. And you can follow me on Twitter if you want. I think that concludes my presentation. Thank you.